Okay. So good morning, everybody. Today we have the speaker of today is Davide Bevacqua. Davide is a PhD student at the INAF Brera. He did his master thesis at the University of Oxford with Michele Cappellari, and then he started his PhD 2 years ago, actually. He's going to finish at the end of this year. Yes. So the PhD fellowship was funded by the INAF Brera ETG12, which is a project basically where all the people here are involved. So the PI is Paolo Saracco, myself, and other people in Arcetri, at INAF Trieste, and other places in Italy. So Davide today will talk about a new perspective on the mass-metallicity relation. Okay? So please, Davide.
Thank you, Francesco. So today I'm going to talk about a different view of the mass-metallicity relation, and in particular, I'm interested in the stellar mass-metallicity relation, and in particular about my focus on quiescent galaxies. So just to give you a brief overview of the talk, I will first briefly introduce what are the quiescent galaxies, what are their properties, and what is the mass-metallicity relation. And then I'm going to present the work I've been doing over the last couple of years. And finally, I will just give you an overview of what I'm doing right now and why I'm in Naples. So first, what are early-type galaxies? They are stellar systems with virtually no features in the optical, and they have elliptical spheroidal morphologies. They are composed by old low-mass stars, and they show no sign of star formation activity, and for this reason they are called quiescent. And typically these galaxies are the most massive and largest galaxies that we know. So we all know that these galaxies have some physical properties, and in particular we know that if we consider their size, velocity dispersion, and surface brightness, these parameters are tightly correlated. They all lie on this fundamental plane, and it's just a manifestation of the Virial theorem. But what I'm more interested in is actually their stellar population properties, so the properties of their stars. And from the light of the stars, for example, we can estimate their ages, and the age of the stars tells us when the stellar component of these galaxies formed. And we can also estimate metal abundance, and essentially the metallicity of these galaxies tells us how efficient was the production of metals during the formation, and how well they could retain these metals and reprocess them into new stars. And in particular, we can also, from the metals, we can also estimate the alpha or iron abundance. And essentially, alpha elements are produced by type 2 supernova, which have short time scales to explode. And the iron elements are mostly produced by 1A type supernova, which have larger time scales. And for this reason, the ratio is essentially an indication of how long was the duration of the star formation. And if you look at these three plots and you focus on the part of this diagram, you can see that the most massive early-type galaxies typically have the oldest ages, metallicities, and alpha enhancement. And on the other hand, at lower masses, on average, these galaxies have lower ages, metallicities, and alpha announcement. And putting all this information together, we came up with this downsizing scenario, where essentially the most massive galaxies form early on cosmic times on shorter time scales, which is the width of this evolution, and in a very efficient way. Here we have essentially the star formation, the specific star formation rate. And on the other hand, lower mass galaxy typically form later. The average formation time is later on cosmic times. They form on longer star formation histories and in a less efficient way. Then, what is the Mass-Metallicity relation, which is the topic of my talk? The Mass-Metallicity relation is a correlation between the mass of galaxies and their metallicity. And though my focus is primarily on early type galaxies, this is true also for star-forming galaxies. And the Mass-Metallicity relation simply tells us that on average, the metallicity of galaxies increases with their mass. And in particular, here I'm showing the stellar metallicity versus the stellar mass, but this is also observed for the gas phase metallicity. And you can actually have the same relation for different proxies of the mass of a galaxy, whether it's the stellar mass, the dynamical mass of or the gravitational potential. And indeed, during the last couple of decades, basically people focused on finding out what is the main driver of this mass-metallicity relation. Here I'm showing the gas phase metallicity against the stellar mass, dynamical mass, and gravitational potential. And to be honest, different works find different results. Somebody find better correlation with the stellar mass, other with dynamical mass, or the gravitational potential. And the problems with this is like more than one, actually. For example, all these parameters are actually interdependent, so it's very hard to disentangle the different effects of each parameter. And but also there are in literature there are different definitions of metallicity used, whether it's the total total metallicity, or the iron abundance, or the oxygen abundance, and also different methods adopted or different models. But beside these problems, when I first started studying the problem of the mass-metallicity relation, I realized that if you look at all these plots, for example, you can see that, okay, the average spread is pretty much similar, but overall the scatter is pretty large and in each of these plots. And for example, although the mass-metallicity relation tells us that more massive galaxies are more metal enhanced, you can see that, for example, if you pick one galaxy here, you can have of 10 to the 11 solar masses, you can have a metallicity lower than this galaxy here, with 2 orders of magnitude metallicity lower and more metal enhanced. And so we ask ourselves, okay, but how representative actually is the average strength of the overall distribution? And so instead of focusing on what is the main driver, the mass-metallicity relation, I started just studying the overall distribution.
Yes. Is this result based on a specific redshift range?
I think this in particular, I'm not sure, but I think it's SDSS. Yes, but as you will see soon, it doesn't depend much on the range. Like the offset, yeah, the 0.0 Yes, but the distribution is always this scatter. Oh, okay, so this is the topic of my talk. To study the mass-metallicity relation and the metallicity distribution, I constructed a sample of quiescent galaxy from the LEGA-C survey. The LEGA-C survey observed thousands of galaxies at intermediate redshift when the universe was half of its age, and this is good because we get rid of half of the cosmic evolution effect. And the spectra are they have a good resolution and signal to noise, allowing for good estimates of the metallicity. And in particular, I selected a sample of more than 600 galaxies, quiescent galaxies, and they have masses between 10.4 to 11.6 solar masses. To estimate the metallicity, I used two methods. The first is the full spectral fitting, and essentially the full spectral fitting compare the observed spectrum with a set of templates, and using a chi-square minimization algorithm, you find the best fit solution as a weighted, as a linear combination of these SSP models, but also to have an independent comparison of metallicity. We also looked at the spectral indices. This is the mass metallicity diagram I obtained, and the stars here are the average values at each mass bins. And as you can see, we recover the mass metallicity relation, meaning that on average, the metallicity increases with the mass. However, as I was pointing out earlier, you can see that while at high masses, we only have high metallicity galaxies. When you go at lower masses, you can have both galaxies with low metallicities and metallicity as high as the most massive galaxies. And on the other hand, you can see that at high masses, we don't have any galaxy with low metallicity. And also you can see that this is like as the mass increases, we start losing galaxies with increasing metallicity. And to highlight this feature of okay, so the average trend is actually due to the lack of these galaxies, and this is what we came up with. We define this lower limit to metallicity. This is just you can see that the distribution empirically define zone of exclusion that we have defined as the metallicity mass exclusion zone or mean zone, and of course the average trend is just in this sense an empirical fact due to the absence of this galaxy here. But of course, this is also depends on an upper limit, on the existence of an upper limit that in this specific case is actually imposed by the prior of our models. And so to verify these results, we look at the spectral indices. And in particular, we use this combination of magnesium band and iron 4383, which is a proxy of the stellar metallicity. And as you can see, the average trend is pretty much the same. We have an increase of the metallicity with the stellar mass. And we also have the same thing that at low masses, galaxy can have both low metallicity and metallicity as high as the most massive galaxies. And you can see that at lower metallicity, we have this mass-dependent lower limit. So at increasing mass, we start using galaxies with higher and higher metallicity. And also, we have that at the highest metallicity, you can see that there is a rather flat upper limit here. And we also looked at, crucially, this results is independent of any models or fitting methods assumed, because it's just spectral indices. And we also find the same results essentially in the literature. This is the gas phase metallicity, and you can see that at increasing mass, we start using galaxies with increasing metallicity, and here we have a rather flat plateau. And has an independent result. We also looked at the prediction from simulation. We asked ourselves, what are the prediction? Are the simulation capable of reproducing these results? In particular, we used the TNG50 simulation. We basically construct a sample mimicking the sample of LEGA-C and our sample of quiescent galaxies, and we adopted similar fitting method. And this is the results. And as you can see, here are the TNG50 galaxies. As you can see, we recover both this increasing mass-dependent lower limit, but also this upper limit to metallicity. But as you can see, the simulation are not able to reproduce very well the lower limit because it's much flatter, and also the upper limit is pretty much the same actually. And we also did the same comparison with Gaia semi-analytical models, and we found pretty much the same thing. And so the first most important take-home message is that looking at the overall mass-metallicity distribution, we realized that the metallicity is actually bounded by two limits: mass-dependent lower limit, which is the mean relation, and an upper limit, which is a flat plateau, which is independent of the mass. And I think this could be very important, for example, for work that develop metallicity evolution models. This could add some stringent constraint to models and simulation, and instead of just focusing on the average trend. The second thing we did is we asked ourselves how the star formation history impacts the observed metallicity distribution. And indeed, we know that at lower masses, we have a variety of star formation histories, while at higher masses, galaxies typically have, they form very quickly, as we saw before. And so maybe different time scales or different way of assembling mass could have affected the observed metallicity distribution. And so our results may be biased or just underestimated. And for this reason, we build star formation histories. These are the star formation histories. Just the here on the left, we have the distribution of the weights assigned by the fit to each SSP. Here we have the input SSP needed for the fit. Here are the best fit models used, and here we have the weights assigned, and this is the star formation history, which is simply a cumulative sum of the weights. And we also constructed this metallicity enrichment history, which basically tells us how the galaxy changed its metallicity over time. For example, here we have that the galaxy over time increased the metallicity. And so we built these curves for all galaxies. We put them together, and we came up with this plot. Here, these two panels on the left are galaxies with stellar masses lower than 10 to the 11, and here more than 10 to the 11. And here in green, we have the star formation history, the average, and 1684 percentiles. And yeah, in red, we have the metallicity enrichment history. And the first thing you can notice is that while at high masses, we always have very short star formation histories. At low masses, we can have both short star formation histories and extended star formation history. And so this is the first interesting point, which is in good agreement with other works. And then we split the sample comparing galaxies with similar star formation history. And you can see that here we span very like one order of magnitude in masses. And you can see that considering that these galaxies have the same star formation histories, you can see that while at high masses, we always end up with high metallicities. At low masses, we have a large variety of metallicities. And so in this sense, we have that the mass of a galaxy is much more important than the shape of the star formation histories to the final metallicity. And then we also compared galaxies with comparable mass, but with totally different star formation histories. And you can see that even though the star formation histories are quite different, the final metallicity, the ranges of final metallicities are pretty much the same. And so in this sense, the observed distribution, the observed scatter that we see, that we observe in the mass metallicity distribution does not depend on how galaxies build their mass. And so this is the second take-home message. The star formation history is not important in determining the final metallicity distribution. The third thing that we check is possible impact of cosmic evolution on the meaning the cosmological evolution. And here in particular, we selected a subsample of maximally old galaxies, which are galaxies that form within the first 3 giga-year of evolution. And this is to avoid possible contamination from later formation. And the first nice thing you can notice is that the mean relation, the lower limit here, is already present just considering the maximally old galaxies. So it means that if it was already in place within the first 3 giga-year of cosmological evolution. And also from, in particular, this plot here, you can see this is a comparison between the average metallicity at each mass bin of maximally old galaxies and the old sample. And you can see that at high masses, basically, there is no evolution of the average metallicity, while at low masses, we have an increase of metallicity over time. And so this means that we have a mass-dependent evolution of the mass-metallicity relation. And yeah, this is their take-home message. There is a mass-dependent evolution of the mass-metallicity relation, and the mean relation is already there at redshift larger than 3, higher than 3. These are all results that I'm hopefully publishing soon. I'm waiting for the referee report. But we also already published another paper where we estimated the alpha virion abundance of a subsample of these legacy galaxies, quiescent galaxies. And how did we estimate the alpha virion? We simply use these two spectral indices. MGB is sensitive to the alpha elements. Fe4283 to the iron abundance. You compare these two spectral indices. In the points here are the observed galaxies, while the grids here are just are the models, the prediction from the models at different. You can see different metallicities and alpha over iron values, and you simply create this grid of values of prediction from models. Then you compare the grids with the observed points. And this is what we obtain. We have that you can see the distribution is peaked at 0.24, which means that most of these quiescent galaxies at median redshift 0.7 are alpha enhanced, and which means that they form very quickly, like their local counterparts. And also very interesting, we compare our sample of legacy galaxies at redshift 0.7 with local observation of SFHs, and you can see that the average alpha over iron is pretty much the same, which is telling us that essentially the alpha over iron abundance has not changed over the last 6.5 gigayear. And yeah, this is the for the last take-home message. Quiescent galaxies at intermediate redshift are alpha enhanced, and there is no evidence of evolution over the last 7.5 gigayear. So what I'm doing now and why am I in Naples? There are 3 main reasons for that. The first is, of course, food. Yeah, this is the first and maybe the most important. Then I'm looking for, next year I need a postdoc for next year, so I'm hoping for a miracle or maybe 2. But the scientific reason why I'm here is that a few months ago I won this archival research visitor program. So I spent a couple of months at ESA, in the stack in the Netherlands, and I looked into the archival data, the early releases of JWST, looking for quiescent galaxies at higher redshifts. And after, I lost almost most of my sight looking for a good spectrum, but after sometimes I could find this this very nice spectrum, which is a quiescent galaxies at redshift 2, and you can see this is very this is the infrared part of the spectrum. It's very shifted, and you can see there are a lot of very nice infrared spectral indices, which is a topic that it's actually not very much explored. So this is a very unique opportunity. And yeah, that's it. Thanks.